This conference will now be recorded.
So, good afternoon, everyone, and welcome back to a fresh new session on market risk modeling. Being day three, it will be the third day of the discussion. And in just before I start, I will just give you a brief perspective of the discussions that happened yesterday. So, basically, what we were talking about was we started looking into the basics of calculus, right? And as a result of this, what we also tried looking into it was that what are the key functions so what are the key components of or what are the key components of the toolkit that we need, right? The uh, we talked about the absolute value function in yesterday's discussion, and one of the characteristics of the function that we observed is that this function has a kink at the point zero, right? So there is a kink to this point, and while there is a kink to this point, so basically this function is not differentiable. So we'll talk about differentiability. This function not a smooth function. It is unlikely that any price or any distribution will follow any of these will follow an absolute or can be summarized by an absolute function. But one of the important points to note over here is that as we talk about these so as we talk about these functions, so this absolute function is very useful for capturing relative changes in the prices, or let's say we're trying to predict the accuracy of the models and so on. So that from that perspective, these functions become extremely useful. So the absolute value function, whenever you want to find out the absolute percentage changes, absolute changes in the returns, kind of return volatility and so on. So basically, when you're looking into to study absolute changes, let's say the absolute changes in the actual versus the predicted value. So that's where this absolute function will be or will become a useful function. Now, functions which can be used to characterize the different distributions, right? Which can be used to characterize the different distribution of the key mathematical variables, or for example, I want to characterize the price changes. I want to characterize the uh, I want to characterize any variable. I want to look at the distribution or anything. So over there, the log function becomes a very useful function, right? So the log function, so there are some specific advantages of a log function. So a log function is, so one of the most important characteristic of a log function is that a log function is defined for the positive values. It is not defined for the negative set of values, right? So for negative values or for zero, the log function is undefined, and we generally look into this. So now the question that comes over here is, so we stopped at the definition of the log function. So let us try to explore the log function a little bit more. Like why is it that log functions are looked into? So why do we all so what are the basic advantages of log function? Now when I talk about the log function over here, I'll talk about the log to the base 10, right? So that is something that we will be talking about. Okay, so over here we have yi is log xi, and also xi is greater than 0 also. So over here we defined the log function, right? So and when we talk about log, we'll always be talking about log base 10. So let us first of all let us see how is it that this log function comes into play. Where where is it that a logarithmic function becomes important? How do I define this, right? So that's something that we would want to talk about, right? So let's start. So one of the biggest advantage that a logarithmic function has, one of the biggest advantage, so one of the biggest advantage that a logarithmic function will have for me is that it helps me smooth down the fluctuations in the data, right? So basically, if I think about it from a mathematical perspective, so let's say I have a value between uh, 100 to 1000, and there are certain fluctuations. The moment I do a log transformation, everything gets so let's say with 10 to 100. Now the moment I do a log transformation, everything, all the figures come between 1 to 2. So it just reduces the figure. So log transformations helps us smooth down the fluctuations in any data set. So if it's be derivatives or be whatever, so whenever you are dealing with a whenever you are dealing with a series, or a time series data, or you're trying to predict the series which is which is a risky, or which has certain extent of volatility to it, it is there that this log function becomes very useful function, right? So that's one. Now the second thing that log function comes in is that log helps us very easily define. A log function helps us define so log functions help us define percentage changes very easily. So over here, let us put down the advantages. The log function has some advantage. Number one, first, the log function helps us in smoothing down the log function helps in smoothing down the fluctuations in a time series. No? Time series. The second is the log function is useful for capturing percentage changes in variables. Right. So these are the two important characteristics that this log function would this log function would have. So let us try to look into certain dynamics. Okay. So let's try to look into some example. Let's try to look into an example. Okay. Let PT be the price of an asset, the price of an asset at time t. Right. So the variable time t, which generates a certain time series variable, it generates a time series variable over the time period, a time series over the time period. Put this time period t equals to 0, 1, 2, dot, 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 t. Okay. So over here, what I'm saying is let PT be the price of an asset which generates the time series. So basically, for P0 at t equal to 0, the price is P0, then it is P1, P2, like this. It goes on. So you have a price series. So you have a whole time series of prices, right? Now over here, so basically, if I am trying to predict the price, right? Now, basically, one of the key objectives of these of the predictions and also is to check the dynamics, or is to derive the objective over here is to mostly to derive the final price dynamics of the variables, right? So if I am to do that, the question is, how do I do this? So I do this using the dynamics, or using the differentials, and try to assess, okay, what are the percentage changes, right? So a an objective, rather, let me put it like this: a key objective of financial analysis, the financial analysis, is to identify the key dynamics of the price variable, of the time series variable, right? Now, because the times now in discrete time, so in discrete time, the dynamics can be captured by the delta pt, right? Be captured by the following formula. So over here, what we want to do is, we have delta pt. Okay, so this is p t plus 1. This is pt minus pt minus 1 divided by pt minus 1. So in a discrete time period, this is the percentage change, right? So this can easily be captured because the time period is discrete in nature. Now, on the other hand, if the time period was continuous, then this would not have been possible, right? So over there, what we would need to understand is, how is it that the price of the asset is changing with respect to time, right? So in that particular case, to specify the prices, so instead of estimating the price, the price trajectory, what I would try to do is, I would try to predict or I would try to make the log of the price series to be more, so to be the target variable, right? So over here, so in a continuous period of time, in a continuous time model, where t belongs to 0 to t. To calculate the sorry to calculate the dynamics, the price dynamics, right? The price function for the price must be the rate of growth of the price must be tracked over a period of time. Right. So over here, what we want to do is, so let's say if the time is a continuous mod, it's continuous, right? So I cannot say that, okay, I cannot, I don't distinguish between time. Let's say the asset price is changing continuously between with time. Like say if you think about an asset market, let's think about the stock index. So prices change every second or every fraction of a second. So in such a case, it is not really possible for us to try to find out the growth of the, so basically it does not become possible, it does not really become possible for us to calculate the price dynamic, so dynamics using the formula that I have given above, using the delta PD formula. So in that particular case, what I need to do is I need to define, or I need to define my target variable of price in a manner such that the growth rate over time can easily be captured, right? So over here, to calculate the price dynamics, the rate of growth of the price must be tracked over a period of time. Therefore, it is convenient to make it to make the target variable convenient to target the logarithmic transformation of price rather than the level value of the asset price, of the asset price. So in a continuous time model where T belongs to this, during this interval, therefore it is convenient to target the logarithmic transformation of the price rather than the level value. So for a very simple specification, a very simple specification is okay. So over here, what we are trying to do is we are saying that PT is equal to log PT. So over here, so the PT is the log of the price. Now, one advantage of using this PT is, or the moment you use this small PT, is that when you are trying to capture the price of the asset, or when you are trying to capture the percentage change, it becomes very easy. So basically, to capture the percentage change in the price, of the asset over time, the log of the asset price is, so basically over here what I'm trying to do is I'm trying to differentiate the log of the price with respect to the asset price. So the log of the asset price is differentiated with respect to the time. So this is done as follows. So this is done as follows. So how do you do that? So now what I say is that there is a very simple equation, or there is a very simple formula to do this. So I'll not go through any derivative. Right? Now, what is this derivative differentiation? The concept of this derivative, or what is this concept of the dynamics? It says that when the time changes, so as time changes by some amount, or by some values, by some delta, the asset prices will also change by some delta. Now, if the time changes by 1 unit, what is the corresponding rate of change of the asset price, right? So that is something, or that is precisely what we call the asset prices, right? So that is what we call the derivative, or that is what we call the dynamics, right? So we will try to frame this concept, like what is the advantage, the key advantage of this. This is so. What is the key advantage of this asset? So basically, it says that if we'll do this intuitively, right? It says that if dt is the change in the, or is the total change in the time period, or is the total change in time, the corresponding total change in the asset price will be, this is dpt. So basically, it says that if dt is the total change in time, the corresponding total change in the asset price will be dpt. Right. Now, the next question, what is this dpt? Dpt is the total change in the asset price, right? So let us try to check how this happens. Right? So what is the total change in this DB? How would that happen? So basically, the way it will going. So basically, if it's a log function, so how does that change look like? So the change over here looks like, so it says that if the time changes by 1 unit, if time changes by 1 unit, the corresponding change, the corresponding total change in the asset price will be dp t dt. So this will be the total change in the price of the asset if the time was to change by 1 unit. So it is dpt. So what is the total change in the asset price? Now this is the log function, right? So now if we differentiate a log function, we get 1 by pt, right? So this shows the following. So it shows, so it shows d, so it shows dpt. Okay. So this shows the dpt by pt whole divided by dt. So what is this dpt? What does the numerator show? So the numerator shows nothing but the percent. So this shows the percentage change in price due to 1 unit change in time period. So this is what, so basically this is what your, or so this is what the percentage changes, or so basically as I was saying, right? So this shows the percentage by which the prices have changed. So basically if I'm trying to capture or predict the log of the values rather than any uh, just rather than just the level values, I can actually capture, or if I'm doing a derivative of it, or when I'm trying to look into the dynamics, I can actually capture the percentage log. So I can actually capture the percentage change in the price, right? So this is why, also this is why it is always easier, or it's very easy to, or this is why the log specification is used for most of the variables. So even when you are trying to do any stationarity analysis or something, so and we have a price variable, the easiest way out is to do a log transformation. The moment you do a log transformation, that part of the story is sorted. And what you have over here is the percentage. So what you have over here is the, so what you can do over here, you can actually capture the percentage change in the price of the asset. So that's the way you can actually identify, or so that's the way you can or you can create or study your the dynamics of the major asset price variables. So over here, I'm saying an asset price. So it could be any asset. So it could be a derivative. It could be any hedging instruments whose prices are fluctuate of any traded asset. So if you are talking about an interest rate, it could be, and you want to assess the you are trying to assess the dynamics of the interest rate, then again you can again take the log of the interest rate and you can work with it. But one thing that you must keep in mind is that the value of the variables for which you are trying to calculate the log values or you are trying to do the logarithmic transformation must not be negative values, right? So this is one. So this is the reason why the log function becomes so important in these exercises, right? So over here, mostly because you are trying to so you're trying to capture the dynamics. That is why log transformations or log specifications become very important in market risk model, especially when you're defining the target variables. Clear? Any questions up to this point on the log function? So then we move on to simulate the log function. Okay, fine. So then let's move on. Let's see how this so how is it that this log function is simulated, right? So how would the log functions look like? So this is we'll use the same set of figures, right? We had used the modulus function. So now we'll use the log function and we'll see how this log function is created and how this log function looks like. Okay. Using the absolute function. So over here, what we'll have is the log function, the logarithm function. We'll say this is the logarithm base 10 function. Which is the log 10. Now over here, what I'll do is I'll introduce an if error. Okay. So now observe one thing that I have numbers between 1 to 10 over here, and in the negative interval, this is negative. So basically what I said is that boss, if this function has an error, just do not do write undefined, but rather division by zero, right? Just give this blank. So it will then take care of that. So over here I see that this is how the function is, right? So one thing you see, let's just check this. I'll do a simple conditional formatting over here on this series. Right, I'll do a simple conditional formatting over here. Okay, so now observe that over here the rate at which it is growing. Just observe this rate. It is growing at a linear rate, right? But over here the number is gradually going at a concave rate. So if you think about this histogram, you can see a concave movement over here. So this clearly shows that, right? So this clearly shows that in this part of the, so basically one thing that we can clearly see is that this function will have, or what we can see in this function is that this function actually helps you out as a smoothing function. So this function helps you smooth it out, right? So smooth out all the variations. So similarly, if you had numbers between 1 to 100, right? So then this number would have, so it would have kind of flattened out more between 1 and 2. So between 1 to, over here between 1 to 10, you are reaching from 0 to 1. So from here 10 to 100, you are reaching to 2. So that flattens out more. So therefore 100 to 1000, you're moving from 2 to 3. So the curve flattens out more. So this graph is a very flattening out curve. So basically this function helps you in smoothing your fluctuations, right? So over here, let's try to construct a graph for this. So this is the variable. So I will plot this function over here. So I will go to insert. Logarithm the variable is. So over here, this comes out, and this is how the graph looks like. So I'll put this over here. So over here, we say that this is figure 02, which is plot of the logarithmic function. Okay, so just let me. So over here, this is x-axis. This is the x-axis. Okay, so over here, what we have is we have the logarithmic plot. So just observe this log function. So up to 1, it remains 0, and from there onwards, it becomes 1. I mean, it there because from there onwards, it gradually increases and then it gradually flattens out, right? So this is how your typical log function would look like. And uh, and one of the ideas, so one of the most important objectives that we generally talk about over here is that when we are talking about the logarithm, so when we are kind of trying to discuss, trying to use explain this function, so what is most important is to understand how exactly is this that this function will be depending, so how is it that it would this function would be on, like what impact would it be having on the variables, right? So we'll talk about that part as well. We'll come to that how or how is it that this model specification would help, or how is it that it would help in the model specifications in this, right? So the next question that comes out over here is that, okay, so we have what we have created up to now is of the log function, right? So is the plotting of the log function clear to us? Okay. Okay. Now we move on to the next part, the third function, which is the exponential function. Right. So how does the exponential function work? The exponential function works this. It's e to the power of x. So example 3. So over here we have the exponential function, so e to the power of x. Now this is a very interesting function. Now because with exponential function and log function together, right, we can actually create a lot of different other functions. So for example, the Gaussian distribution or the normal distribution function, the normal distribution is created using e to the power of x, right? So that has e to the power of x over there. However, another important concept is that so basically it is used to demonstrate a very a very symmetric kind of a function and with x minus mu by sigma whole square. So exponential functions are used to describe functions or those paths where the variables grow at a constant rate over time. So basically, if the percentage of growth of a value of a variable is constant over time, then what you use is the so there what you use is you use the exponential function to describe that path. So to describe that path of the variable. So for example, exponential functions are widely used for uh, microbiology problems because the the microorganisms have a constant rate of growth, right? So they grow, the percentage changes or the percentage rate of growth is over a period of time is constant. They have a very constant rate of growth over the period of time. So this is one part of the story. Now the question is that if you use the log function and the exponential function together, right? So it can help you. It can help you create. It can help you create a log normal distribution, so which is one of the most important distributions which is used in mathematical finance. Most of these most of these assets in the asset market. So be it the stocks, to some extent, or be it uh, be it the other assets, right? So they follow the log normal distribution. So that the log normal distribution or an S-shaped distribution is a very important part of, or it's a very important component of market risk analysis, and that's something that we need to study. Right. So before we go out to that, so let's try to see where is so why is exponential function so important, and how is it that exponential functions and the logarithmic functions interrelate. So it is generally seen that that the exponential functions are or exponent or the to the power of x functions are an inverse of the logistic of the logarithmic functions, right? So on one hand, or so one of the important questions that we'll have is we need to understand how to talk about or how to get to this uh, path. So basically, think about it this way. Let's say there is a variable x which grows at a constant rate, right? Then what I do is, so then if I differentiate it with respect to time, so let's say I differentiate its percentage with respect to time, and that is a constant. Then when I'm trying to calculate this back, so when I try to calculate it back, you will see that the path that that variable follows. So let's say over so in the above example we used the example this example of log pt, right? So over here you are seeing I've talked about PT's it's log PT. So therefore, if I do so if I want to find what is PT, so PT is nothing but e to the power of something. So it follows an exponential path. So variables which follows an exponential path have a constant growth rate, right? And if the growth path or if the growth dynamic is exponential in nature, what it means is that the path of the variable is mildly explosive, or that variable is not growing more than exponentially, or as we call it, hyperbolical, right? So from this growth rate, from the type of the pattern that the growth rate follows, right? We what we'll try to do is we'll try to find out, or we can actually create that asset path which shows that, so which shows whether the which helps us calculate the path of the asset. So similarly, this kind of a relationship, so these two functions become extremely important because of two reasons. Number one, log this logarithmic and exponential relationship is explored in the Black-Scholes modern model. It's explored in the BSM model and in the Ito's lemma. So, so the entire proof of that Ito's lemma, from where you are deriving that asset path, is or the path of that price of that asset. So that entire Ito's lemma part is a very critical part of the Black-Scholes model, and that's where these two functions become very important, right? So therefore, so let's try to look into the exponential function, and let's try to go a bit more deep into this function, right? Because we need to understand this function. Okay, fair enough. So let's try to define this function first. Okay, so just what I'll do is I'll copy this part from here. Okay, so let x and y be two real variables. Other the y belongs to R. This function is an exponential function. Exponential function f of x to y is a rule such that for each xi belongs to x and yi belongs to y, the following is the rule. So over here, what we'll do is we'll go to equation. We'll say e to the power of so what we'll say is e to the power of x. X belongs to x belongs to R. So this is well defined for any real numbers, right? So this is what the function is. Now, now there are some important relationships which must be taken into account if you are talking about the if you are talking about the exponential functions, right? So there are some important relationships. But before we go into the relationships, let's try to assess how this exponential function would kind of look like, right? So let's go back. The exponential function. So in this exponential function, so the exponential function over here is something like this. Right. So over here, what we have is, okay. Okay. So now for the exponential function over here, one of the things that you can clearly see is that the function, or I mean, this function has started to grow from mostly from this point. So basically, so when this number becomes, when it exceeds, so you see that up till 3, right? This has not increased so much. So between 2 to 3, the function more or less remains like that. But from 4 onwards, right, this function has started increasing in an explosive manner. So which shows that for an exponential function within a limit, the function behaves more or less stably. But after, like, once the account has, once it has started going up, right? So once it has kind of started, so once it has kind of started going up, so one of the important checks that you get to see is that the function starts becoming explosive. So after a point of time, this number will start becoming explosive, right? So this is how an exponential function typically looks like. So one thing you can see is that this function tends to have highly nonlinear properties. Right? So Okay. So one of the important one of the important observation that I would make from this exercise is that if you are to model a nonlinear function, now I think this is no new revelation though, but it's a very basic thing that if you have to model some of of a if you need to or if you want to model a nonlinear function, then what you need to do is the easiest way to do that is to use an exponential function, or have a behavior inbuilt which is which is representative of an exponential function, right? So that's something that we need to look into. Right. So exponential functions become very useful for developing these nonlinear models. And one of the important characteristics of a nonlinear function is, or of this exponential function is that if the variable is growing at a constant rate, then the path that that variable which is growing at a constant rate follows is exponential. So from the logarithmic functions, it can be directly backtracked and this can be identified. Right. So So this is the y-axis. This is the x-axis. Okay. So this is the third type of a function. Right. So is this plot of the function clear to us? Okay. So now let us very quickly look into another important characteristic. So okay. Now so let's think about this one. Right. So how do I define this, or so over here I want to talk about the relationship between the log functions and this exponential function, right? So there are a few points that we would like to know. So exponential functions, or any variation of an exponential function, and exponential functions family of functions are extremely useful for modeling nonlinear methods, nonlinear variables. So basically what I'm trying to tell you over here is that this is one of the functions which will always become handy, right? So you have an exponential function, you're doing that exponential plot and so on. So the exponential functions of any variable or the exponential family of functions actually used for modeling nonlinear variables. Now for sufficiently large values of the independent variable, the exponential function can develop extreme nonlinear behavior and hence becomes important in the domain of the market, in the domain of market. Now, while I talk about this exponential function, we need to mention or we need to talk about its relationship with the logarithmic function. The exponential function is very closely related to the logarithmic functions. The since the former is an inverse of the latter. Inverse of the latter, that is the logistic function. Latter and vice versa. So basically, over here, the exponential function is closely related to the logarithmic function, since the former is an inverse of the latter and vice versa. So similarly, if exponential function is the inverse of the log function will also be an inverse of the exponential function, right? So that's the next part. Now, what I mean by it, to very simply understand. So let's say I have said that the log of 1 is 0, right? Therefore, the so if I want to obtain back that value 1, so e to the power of, so log 1 has 0. Now, if I want to find out that value of 1, so that value which has led to this value 0, the log value. So what was that value of x which has led to this log x of 0? Then it is the exponential function. Observe that the exponential of e to the power of 0 is 1 and log of 1 is 0. So the in logarithmic functions, the inverse of the logarithmic function is the exponential function. So let's say I want to find out that the log of 2 is 0. So there's a value 0.301 after log transformation. So what is that value which has led, what is that value of x which has led to this value of log? So basically what we say is it is exponential of this value. So the log of 2 is okay. So this is not coming exact. I think it's something to do with the base. I'll just check that one. I'll check on that. So basically the inverse. So basically what I was saying is that let's say I take this. So at 1 the value is 0, right? So I'll put the exponents of 0. It returns 1, right? So similarly, I have e to the power of 1 over here. Okay. Okay, so fine. So one of the thing that we can, so that one of the things that, so I'll just check it with all the other values. So I think I'm missing out something basic out here. So just let me get back to you in the next class on that. Okay. So the exponential value over here is, so as I said, that exponent, the e to the power of x is the inverse of the latter and vice versa. So now one of the next thing that we'll need to do is that, okay, so if this is the, so like if it's the inverse, so then let's say I have so one of the observation that, so let's put down one, so I'll just put down one more observation over here, that if a variable grows at a constant percentage rate over time, then the path of that variable, so that the path of that variable is exponential. Or let's put it this way, then the variable follows an exponential trajectory. Follows an exponential trajectory, right? So over here, how do we show that? Now this can be shown as follows. So this can be shown as follows. So let's say I have this percentage growth rate, right? So suppose the growth rate of an asset price is constant over a continuous period of time. So the asset price is growing at a constant rate, right? It's continuous over a continuous interval of time. Okay, over a continuous period of time. Right. So let's say it grows at a constant rate a, where a is greater than 0. So let's say this variable grows at a constant rate a. Right. So now the question is that what path does this PT actually follow? So what path does the asset price follow? So, so the path of the asset, the path of the variable PT will be the path of the variable PT will be so let's try to put it here. So this is D to dpt by dpt by pt, which is equal to dot dt, right? So now over here, the next thing that we do over here is if we integrate this. So let's say I integrate this entire thing over a period, right? So then from there I'll get this as, if I integrate this as, I'll get this as log pt, and that will be some a pt dt, right? And then, or at, and then at plus c, and then when I take the log of the when I try to get to that t, I'll take the exponent of that, and then it will become e a to the power of t. Right. So let's say integrating both sides. So integrating both sides, what you will get is, I'm not doing the integration manually over here because I presume, because I have two engineers, I presume integration is like was a bread and butter at a point of time, right? So so this is log pt is equal to, okay, so I have 80 plus some k, where k is a constant. K is the constant of integration, right? So over here, so integrating both sides, this is what we get. Okay, so I have India. So the path of the variable pt will be this, and we integrate both sides. So k is the constant of integration. Now to reach to the path of that, so over here, so the pt becomes, so this is e to the power of at dot e to the power of k. So e to the power of k. Now this e to the power of k is called your constant of integration. So this e to the power of k is, or let this be, where a equals to e to the power of k, the constant of integration. So this is the constant value, right? So over here, one of the things that we can clearly see is that the asset, so whatever, so given that the asset price is growing continuously, the path that this equation of this follows is exponential in nature. So basically, exponential path. So if I say that the variable's path is exponential, it does not mean that. It does not mean that there is some explosiveness or something around. All it means is that the asset grows at a constant rate throughout the time period. Now the challenges will happen, or you know, I mean, extreme non-linearity will appear for this function when the asset price starts growing non-exponent. I mean, when the asset price starts growing exponentially. So instead of a, the growth rate is e to the power of a, then this asset price itself will be growing hyperbolically, right? So when the asset price, the price of the asset, it grows itself over a period of time, then what you say is that, so then we often say that the asset prices are going through a bubble, or asset prices are way beyond their fundamentals and stuff, right? So therefore this exponential function again is an interesting way to model unstable or explosive asset prices, and thereby try to capture the risk. So that's that very next part. Using the log and the exponential function that we have discussed till now, the next part that we'll be doing is we will be building up an asset price dynamics, right? And we'll build up an asset price dynamics, and we'll see what are the key characteristics and how do we assess, or how is it that mathematically we can assess the instability in the asset prices, right? So that's the very next part of the discussions that we would have, right? So let's take a pause here for the day. I let me share over these documents, go through these basics. So this week we just wanted to get the ball rolling, and that has been done. So we could do that. So we have introduced to the basics of functions. We have explored a bit of the functions around, and now we'll see how to apply these functions in a real market risk scenario, in asset pricing, in derivative pricing, and what are the areas where this exponential and the logarithmic function would come to play, right? So we'll explore that. We'll explore the log normal distribution as well to some extent, and from there we'll move on to talk about one more function, which is the greatest integer and the sine function, SGN sine function. These are the two functions that we'll talk about, and from there we move into the next part of calculus, which is our limits and continuity. Right? So that's the next part of the discussions that we'll have in the next session. So let's meet up next weekend, and then let's get the ball rolling. Thank you. Thank you, guys. Thank you for your time. Stay safe and have a great week ahead. Bye bye.